Hello, and welcome to this presentation on conditional probability. My name is Dipanshu Davande, and this is part of my Com 533 coursework. Over the next few minutes, I'll guide you through the basics of probability, explore conditional probability with examples, and highlight its real-world applications. So let's begin. To understand conditional probability, we first need to grasp the broader concept of probability. Probability is the mathematical language we use to quantify uncertainty. Its origin date back to 17th century, where mathematicians like Blaise Pascal developed it while solving gambling problems. Pascal's work laid the foundation for modern probability theory, which is now fundamental across fields like statistics, physics, economics, and more. In daily life, probability is everywhere, whether it's predicting the weather, modeling risk for insurance, or even guiding artificial intelligence in decision making. Think about how many times apps have provided prediction based on probabilities like traffic delays, product recommendation, or even medical diagnostic. It's worth reflecting on this question by Pascal. Is it probable that probability brings certainty? This underscores the delicate balance between uncertainty and informed prediction. Building on this foundation, let's focus on a specialized aspect of probability, conditional probability. Conditional probability answers the question, what is the likelihood of an event occurring given that another event has already occurred? To put this in perspective, this is the formula. It reads as P of A given B is equal to P of A union B divided by P of B. This concept refines prediction by incorporating new information. For example, knowing that it's raining increases the likelihood that someone will be carrying an umbrella. This adjustment, which is based on context, is the core idea behind conditional probability. To visualize this, let's take a sample space S, uh, and let's take another event A. If you wanted to calculate the probability of event A happening in this sample space, we will just calculate the possibility of A under this whole sample space. We'll just count the number of outcomes of A like that. But what if there is another event B happening and we are asked to calculate that we know that B has happened. Now tell us what is the probability of A also happening. So in this case, we need to focus on this common area between A and B, and we need to calculate the probability of A happening in this region, knowing that B, the orange circle, has already happened. In this case, we are basically transforming our sample space from the bigger rectangle to this orange circle over here and finding the probability of A in this circle. So we know that in this circle, the common area only, the yellow part only signifies the occurrence of A when B has occurred. To uh, to make this concept more concrete, let's look at an example. Imagine rolling a standard six-face die. Here are the two events I'll consider. Event A being getting a number less than 4, and event B being getting an odd number. So to put it in perspective, event A will have the three possible outcomes, 1, 2, and 3. And event B will have also have three possible outcomes, 1, 3, and 5. To calculate the probabilities of A and B with the given information would be fairly simple, as both have three possible outcomes out of six total outcomes. The probability becomes 1 by 2 for both of them. But with conditional probability, what we are aiming to answer is what is the probability of A happening when B has already happened. To make it more simpler, we are trying to calculate what are the odds of getting a number less than 4 if we know that an odd number is already rolled in the die. So let's look at it mathematically. So, given here are the six possible outcomes for rolling a die: one, 2, 3, 4, 5, and 6. So, let's put it in a bigger sample space. These six outcomes will be distributed randomly in the sample space. Now we are taking two events. Event A consisting of 1, 2, and 3 outcome, and event B consisting of 1, 3, and 5 outcome. Now, if we fuse all these events in sample space together and consider the overlaps which are present in them, we will get a Venn diagram which will look like this. So this Venn diagram clearly indicates that A contains only 1, 2, and 3. B contains 1, 3, and 5. 4 and 6 does not belong to A and B. That's why they are lying outside. Also, the common area consists of 1 and 3 as the common outcomes for A and B. So to calculate it mathematically, let's move it to the side. We already know the probabilities of A and B as we calculated in the previous slide. So we'll write it that way. We need to calculate the probability of this yellow region there. So since we know there are two possible outcomes, 1 and 3, out of a total 6 outcomes, the probability of A union B will be 2 by 6, which will be simplified to 1 by 3. Now we have all the data. If we put it into the formula of conditional probability, we get the probability of A given B is equal to 1/3 divided by 1/2, which is equal to 2 by 3. Now, what does this number 2 by 3 actually mean? To make it simple, it tells us that there is a 2/3 chance of getting a number less than 4 if the die rolls an odd number. So it means that if someone rolls a die and tells you that I have gotten an odd number here, so tell me what is the probability that the number I have on the die is also less than 4. So in that scenario, you can say that there is a 2/3 chance that the number on the die is less than 4. Conditional probability has various real-world application. For example, in machine learning, algorithms use conditional probability to classify data and make prediction. For example, in this one, spam filters calculate the probability of an email being spam based on features like the presence of words such as when, urgent, or a hyperlink, and then calculate the conditional probability based on that on the features present in the email. And where in the end, we'll calculate the argmax to get whether the email is a spam or not. Other examples include medicine, finance, and basically everyday life. As these examples show, conditional probability is woven into many aspects of modern life, helping us make smarter and data-driven decisions. To conclude, conditional probability is a fundamental concept in mathematics with applications that reach far beyond theory. Whether it's used in AI, healthcare, or everyday decision making, this tool empowers us to make better decisions and navigate uncertainty more effectively. Thank you for watching this presentation. I hope it has been both informative and engaging. Thank you.